In the organic chemistry sequence, we will learn to deconstruct, or reduce, seemingly impossible molecular concepts and pathways into smaller, more manageable pieces. We should recognize that big scientific problems are really a collection of smaller problems. Once it sinks in, we are able to take a systematic and organized approach to the huge subject of organic chemistry. At first glance, 2 semesters of organic can look like a giant mountain, like Everest. We have to decide on how we are going to conquer that mountain, get to the top, and come out the other side learning from the experience. The approach to be presented here works for most people who come into organic knowing the basics and who are willing to work hard. Climbers don't just show up to Everest and start climbing. They develop a plan beforehand, they organize equipment and logistics, and plot a route that they hope will take them to the summit. Climbers then begin at base camp, for us that's the general chemistry sequence, and take a measured, careful approach up the mountain. They start with the straightforward sections first, for us the first few chapters of our textbook, and reflect on their progress. Once they have cemented that success, they move on to more challenging sections of the mountain, using whatever they have learned so far. Each section certainly becomes more challenging, however their planning and practice, and learning from failures along the way, usually results in overall success. We will do the same in organic chemistry. We start at base camp in general chemistry, and then add knowledge of organic concepts and structures, until we are ready to hit the hardest sections. For many, this will be when we begin reaction mechanisms in Chapter 6. Climbing mountains is a scary business, but we can succeed with base knowledge, practice, stamina, learning from small failures, and a willingness to develop our skills as we go. During the 2-semester undergraduate organic chemistry sequence, we will show that the subject relies on a fairly limited number of core concepts. The periodic table is the same one used in general chemistry, and you should come into organic understanding how it is organized. From there we will expand on your understanding of topics, such as electronegativity, valence, and the octet rule. Most importantly, we will develop a real understanding of bonding, and which elements prefer covalent, ionic, or somewhere in between, for their bonding patterns. We expand on those ideas by exploring what organic molecules look like, where they might be reactive, and how they try to stabilize any charges. Organic has its own vocabulary, and we develop that gradually through each chapter, with many of these new words taking some effort to assimilate. Once the foundation has been laid over the first 5 chapters, we move into chemical reactivity and apply the concepts studied earlier. The understanding of chemical kinetics and thermodynamics will be strengthened, and the use of reaction profiles introduced, as a way of visualizing energy changes in chemical reactions. Once those ideas are solidified, the study of chemical mechanism begins, with each of the concepts studied so far playing an important role. From there, we take a methodical approach to studying over 120 reactions, many of which also occur in biochemistry or are used in the chemical industry. Success in organic chemistry relies on coming into the course with a solid foundation from general chemistry, and then being willing and able to build on that knowledge. While organic chemistry may look like Everest at first, it is possible to get off to a good start by being organized in your thoughts and in your approach to the subject. If you were shaky on some of the basics in general chemistry, you must get them sorted out immediately in the organic course. Since the whole course relies on these ideas, it will be impossible to do well if they are not solid. You have already seen periodic trends, types of bonding, and molecular shape before, so review that material before the semester begins. You must understand valence, how many bonds an atom can make, based on the octet rule, and when atoms will be charged, either negative or positive. It is essential to know which atoms will carry lone pairs, as they are the electron glue that will be used to make many new bonds. Knowing about electronegativity allows us to map out dipoles in molecules and identify areas of electron excess to be known as electron-rich and electron deficiency to be known as electron-poor. As we begin putting these ideas together in the acid-base chapter, we will discover how well you understand pH and what the pH level means in terms of what kinds of species will be allowed in specific reaction environments. Success over the first 3 chapters in the first semester will serve as a good idea of how well a student will do for the rest of the semester. While organic chemistry is certainly based on the same principles as general chemistry, there is one important difference that must be appreciated early on and kept in mind as the subject progresses. General chemistry is often seen as a linear progression through topics, with little feedback into earlier material. As such, you study topic A, move on to topic B, then C, etc., sometimes with little direct overlap between each topic. Organic chemistry is more like an interconnected network, in which a small set of core concepts is used repeatedly to explain most of the problems encountered. For example, the simple size of an atom, which reflects its ability to hold a negative charge. This will be used to connect material from the early acid-base chapter to highly complex reaction pathways, encountered at the end of the second semester. None of these core concepts can be avoided if a student wants to be successful in organic chemistry. Before coming to the first class in organic chemistry, you must do some review of general chemistry basics. While memorizing some information is a minimum expectation in any subject, the application of concepts is more important in organic. This starts with the periodic table. You do not have to memorize all the elements, that's pointless. You do, however, need to know roughly where the important elements are and why they are there. Metals to the left, non-metals to the right. Periodic trends, such as atomic size and electronegativity, are key to understanding why and how atoms and molecules react, so you need to be on top of those trends. We will find very quickly that using electronegativities to predict dipoles within molecules will be essential for predicting where and why a molecule reacts. You must therefore be secure in predicting bonding patterns from electronegativity differences. To begin your preparation for organic chemistry, you should look at a periodic table and make sure you are comfortable with how it is organized. The Russian chemist Dmitry Mendeleev suggested that elements could be organized based on their periodic relationships, which proved to be a huge step forward in how chemistry could be explained. Addition of more elements over the years proved Mendeleev to be correct, and the modern periodic table is now considered a master code that can help us solve problems and also predict new chemistry. From your general chemistry studies, you should know that the metals on the left give away their valence electrons to become positive ions, known as cations. Conversely, elements on the right prefer to accept electrons in order to fill their valence shells and achieve an octet. Elements in the middle are flexible and may share electrons to form covalent bonds. When elements are organized in groups vertically, their valence electron count is the same. For example, lithium, sodium, and potassium all have one valence electron. Elements arranged in rows, horizontally, increase the number of electrons in their valence shell by 1 as we move from left to right in the table. As we add more electron shells, atomic size changes. So, as we head down the periodic groups, the atoms get bigger. For example, fluorine is very small, but in contrast, iodine is very large. This will have profound consequences on bond strength later. A great place to begin preparing for organic chemistry is to pick up some electronegativity values of the most relevant elements. The Pauling scale used here is convenient for this and not difficult to memorize. In fact, the most used elements differ in increments of 0.5. Starting with lithium on the left at 1.0, going across to fluorine on the right at 4.0. Once you have a firm grasp of electronegativity values, they can be used to predict bonding patterns, such as covalent and ionic, as well as electron distributions in dipoles. Knowing where electron density is within a molecule is key to understanding its reactivity. Once we have electronegativity values on board, we can begin to understand bonding characteristics between different atoms. Elements with very different electronegativity values, meaning they have a very different attraction for electrons, will form ionic bonds by electron transfer. The simplest example of this would be sodium chloride, or common table salt, in which the sodium has transferred its one valence electron to chlorine. The elements have very different electronegativity values, with chlorine being much more attracted to electrons. Sodium giving away its one valence electron, and chlorine picking it up, results in both elements achieving the valence octet. As such, there is no line drawn between sodium and chlorine, and this purely ionic molecule is represented as ions, or the reduced form, NaCl. Applying this idea to carbon and hydrogen, the two most common elements found in organic molecules, we find that covalent bonds make more sense. For example, in methane, CH4, the carbon atom needs 4 electrons, and hydrogen needs 1 each. Since they have similar attractions to electrons, which is quantified by their similar electronegativity values, carbon and hydrogen will form covalent bonds, in which the valence electrons are shared. Carbon needs 4 electrons to satisfy the valence octet, while hydrogen needs 1 each. Therefore, one carbon shares electrons with 4 hydrogens, to give the covalent bonds observed in methane. Once we have an idea of bonding modes, we can begin to look within molecules to identify dipoles and areas that are electron-rich or electron-poor. This is one of the most important ideas in organic chemistry, and will be used to explain how and why most of the reactions studied occur the way they do. Electron imbalance occurs within covalent bonds between atoms of differing electronegativities. The less electronegative partner will be electron-poor, while the more electronegative element will be electron-rich. This example of the simple alcohol methanol, We'll explain why the hydrogen is acidic and susceptible to attack by electron-rich bases. The highly electronegative oxygen pulls electrons away from the less electronegative hydrogen. This makes the hydrogen electron poor and therefore attractive to electron-rich species, such as bases. Electronegativity values will also help explain why hydrocarbons, like methane, are not acidic. Since the electrons are about equally shared between carbon and hydrogen, there is no area of electron deficiency to attract an electron-rich base. As we develop acid-base reactivity, we will find that a dipole involving hydrogen correlates with that proton being acidic. In these examples, methanol will react as an acid, but methane will not. In a more general sense, being able to identify areas of electron excess and electron deficiency will go a long way to helping explain where molecules react under different conditions. For example, in the carbon to oxygen double bond, the electrons are much closer to O than C, which is shown using the delta plus and delta minus notation. Any electron-rich reagent will be attracted to carbon, while any electron-poor species will go to the oxygen. We can also invoke dipoles to help explain physical properties of molecules. Using methanol as an example again, we find that its boiling point is around 65 degrees Celsius, while that of methane is negative 162 degrees Celsius. The dipole in methanol means there are areas of electron deficiency, shown as delta plus, and areas of electron excess, shown as delta negative. This is not the case in methane. This will result in stronger intermolecular forces of attraction between molecules of methanol than are possible in methane. Add in the ability to hydrogen bond between the oxygen lone pairs in methanol and protons on other methanol molecules, which is not possible in methane, and we have a rationale for why there is over a 200-degree difference in the boiling points. This kind of analysis will also help explain molecule solubilities once we start planning how to set up reactions. If we consider how the methane molecule might be constructed, we need one carbon atom, with 4 valence electrons, and 4 hydrogen atoms, each with 1 valence electron. Combining these atoms should give a molecule, in which each atom has the desired electron configuration of a noble gas. However, there is an obvious problem with this model, as methane has 4 equivalent single bonds, holding the carbon and 4 hydrogens together. This is not possible if carbon is simply using its valence orbitals, the 2s and 2 of the 2p orbitals, since those orbitals are not equivalent in size, energy, or shape. We need a better model. It is now accepted that carbon uses hybrid orbitals to make bonds, in which the s and p orbitals mix, or hybridize, in order to get to stable molecules. In methane, the molecule adopts a tetrahedral shape to maximize the distance from each bond, and this requires a tetrahedral arrangement of orbitals. If we draw the valence electron configuration of carbon as an energy diagram, we are able to visualize the problem more clearly. A paired-up set of 2s electrons and 2 individual p orbitals are not able to interact with 4 hydrogen atoms and form 4 equivalent bonds. So, if we need 4 equivalent bonds, we need 4 equivalent orbitals. Mixing the single s and the 3p orbitals gives us 4 equivalent sp3 atomic orbitals. These orbitals are an average of the s and p energies and shapes, and project out from carbon in a tetrahedral rearrangement, as expected from VSEPR theory. When we line up the tetrahedral carbon atom to bond with 4 hydrogen atoms, it becomes obvious how this works. The hybrid orbitals on carbon are atomic orbitals that overlap with the 1s orbital on hydrogen to form molecular orbitals. The tetrahedral shape and the associated bond angles of 109.5 degrees are not a coincidence, as this shape would be predicted by valence shell, electron pair, repulsion theory to be one that minimizes the interactions between each bond. Hence, we have accounted for the bonding observed in methane. The sp3 model works for carbon, nitrogen, and oxygen atoms that only have single bonds attached. Using the configuration of carbon as a platform, it is simple to get to sp3 nitrogen, for example in ammonia, by adding 1 more electron. Oxygen in water and alcohols is explained by adding 2 extra electrons compared to carbon. In general, carbon, nitrogen, and oxygen atoms displaying only single bonds are explained using the sp3 hybridization model. As we progress to alkenes and alkynes later in the first semester, we will need to go beyond the sp3 model to include the need for pi bonds. As a preview, 1 pi bond means the need for 1 p orbital to be set aside, so the sp2 model will be needed, while 2 pi bonds needs 2 p orbitals, which means the sp model. As with each of these major topics, you will find more detail, linked through hyperconjugation.com. We will spend time, in the first few weeks of the first semester, learning how to reduce organic molecules down to bond line structures, with only the functional groups being drawn out in detail. Then in general, the main shapes to be encountered in organic chemistry will be tetrahedral, trigonal planar, and linear. While these shapes are based on carbon groups, it is easy to extrapolate to nitrogen and oxygen by recognizing that these atoms inherently bring with them a lone pair or lone pairs that neutral carbon does not have. As such, lone pairs will repel bond pairs and alter molecular geometries slightly away from perfect tetrahedra, for example. Drawing in lone pairs on molecules will be key to understand where molecules will react with electron-poor species. You should get into the habit of including lone pairs on any atom that has them, especially nitrogen, oxygen, sulfur, and the halogens. Once we are comfortable with bonding patterns and lone pairs, we begin looking at situations in which atoms within molecules become charged. We need to develop an understanding of what constitutes a stabilized or a destabilized charge, in particular on carbon, nitrogen, and oxygen. In the first half of the first semester, we focus on how molecules deal with negative charges and deal with positive charges on carbon later. It should be obvious by now that atoms that are more electronegative will be okay accommodating a negative charge since they are attracted to electrons. Additionally, larger atoms tend to accommodate negative charge better since they are able to spread the electron excess over a larger surface area. Therefore, a negative charge on sulfur is more stable than a negative charge on the smaller oxygen. This will have profound effects on conjugate base stability when we get to the acid-base material. Now, we look at one of the most difficult topics covered early in the first semester, the delocalization of charge through pi systems. When we consider the two anions shown here, both have negative charge on carbon. And because of carbon's middling electronegativity, we expect both anions to be very unstable. However, the allyl anion, on the left, is significantly more stable than the alkyl anion on the right. It is obvious that the pi system must be playing a role in this difference. When we expand the first structure to include the pi system, it appears that the anion may exist in a p orbital that is able to be in line with the alkene pi cloud. This is how we explain the greater stability of the allyl anion. The charge in the allyl system may spread out, which makes it more stable. The fact is that the anion structure is somewhere between these two pictures, with both carbon-to-carbon bonds being of equal length. The resonance structures shown represent where the charge can delocalize to. However, it is important to recognize that these two images are not separate molecules. Resonance is not equilibrium, in which one molecule turns into another. It is a method for structures to be stabilized by spreading electron clouds over several atoms. Instead of drawing orbitals out every time, we use abbreviated bond line structures, such as those shown here, with the actual molecule looking somewhere in between. A more accurate image, known as the resonance hybrid, shows where the charge can delocalize, and this image is more often represented using the delta notation to show where the charge is spread to. The allyl anion delocalization pattern may be applied to any anion next to a pi bond. When we begin our study of acids and bases in organic chemistry, the ability of carboxylate anions, an example of which is presented here, to delocalize the negative charge, will help explain why carboxylic acids are so acidic. As we progress through the second semester, electron delocalization becomes a major theme in mechanisms, for example in the formation of resonance-stabilized enolates. It doesn't matter what atoms are involved, negative charges are stabilized by delocalization. Mostly in the second semester, we will encounter positively charged species that also benefit from delocalization. As an example, the opposite of the allyl anion is the allyl cation, which exclusively involves carbon atoms. In this species, the pi bond electrons are used to help stabilize the electron deficiency in the carbocation. This is represented by an empty p orbital, and the molecule is stabilized by spreading that deficiency across several atoms. Similarly, a very important species in the second semester is the heteroatom-stabilized carbocation, in which an atom with a lone pair is able to help stabilize an electron-poor carbon. It has been said that the second semester of organic chemistry features the same mechanistic events as the first term, but with extensive delocalization of charge and intermediates. Therefore, it's a good idea to become comfortable with delocalization patterns as soon as possible. Once we have the foundational material understood, we move on to our first actual reaction type in the organic chemistry sequence, acids and bases. While the definitions and ideas are the same as in general chemistry, we must deal with a lot more detail, and many more examples, in the organic world. From the Bronsted-Lowry definition, a base accepts a proton, and an acid delivers a proton. While these definitions work for protic acids, we will broaden the conversation on acid-base ideas by using the Lewis definitions. Here, any electron-rich species is a base, and any electron-poor species is an acid, and capable of accepting electrons. The generic example shown here shows an electron-rich base, labeled as B, reacting with an electron-poor acid, Ha. As in general chemistry, the proton is transferred from the acid to the base, and the conjugate acid, BH, and conjugate base, A-, are formed. In organic chemistry, we dig deeper and ask why and how this reaction occurs, as well as answer questions about equilibrium and the populations of the different species in the solution. To begin digging deeper into the how and why reactions work, we begin by considering this generic acid-base reaction. We ask what needs to happen during this conversion, in terms of bond breaking and bond forming events. This question will be the first one we go to during the study of over 120 reactions in the organic sequence. As is the case with many of these reactions, we need to ask where a negative charge will be most stable, as that often dictates the outcome of the process. One of the deeper issues we must consider in studying organic reactions is why the molecules want to react in the first place. In the large majority of cases, the inherent reactivity will be explained by considering dipoles in molecules, which act as areas of electron excess and electron deficiency. For a simple acid-base reaction, the base with its lone pair is electron-rich, while the proton usually is electron-poor due to the electronegativity of the A atom or group. So there is an inherent electrostatic attraction between a base and an acidic proton. Now, we must focus on how to describe that communication, as well as the bond-forming and bond-breaking events that lead to the conjugate acid and base. The British chemist Sir Robert Robinson suggested a curved arrow notation to describe the movement of electrons that is now used across the world to represent changes in organic reactions. In an acid-base reaction, there are only two events occurring: formation of a bond between the base and the proton, and breaking of the bond between the proton and the conjugate base. Therefore, we only need two curved arrows. We know from the bimolecular rate equation that these events occur at the same time, so the mechanism involves one arrow from base to proton, and a second arrow from proton to the conjugate base, A. Notice that both arrows begin at an area of high electron density, the lone pair on the base, and the bond between the proton and A group. The arrowheads are used to describe where the electrons are being pushed to. The arrows are an elegant way to describe a lot of dynamic change in a chemical reaction. They infer that the species are approaching, with the dipoles lining up to match, and facilitate the making or breaking of bonds. There are many hundreds of these arrows across the organic chemistry sequence, so it is essential that you become comfortable with their use as early as possible. While we study acid-base chemistry early in the organic sequence, in order to transition from general chemistry, and also get a taste of the detail level expected, we will need acids and bases as reagents throughout the course. We use the simple proton transfer process to learn about anion stability, where charge will prefer to be, and to get an idea of how equilibrium works. These ideas will be used across the 2 semesters to predict which anions will be preferred in any situation, and whether a reaction will be reversible or not. Starting here with a reaction between a nitrogen base and an alcohol acid, the anionic nitrogen accepts the proton and converts to the neutral amine and the alkoxide conjugate base. The reaction is known to be strongly exothermic, which tells us that the products are way more stable than the starting materials. In fact, the equilibrium constant for this reaction is in the region of 10 to the 22nd power, which means that the right-hand side is completely favored, and the reaction is irreversible. Why is this so? Since nitrogen and oxygen are neighbors in a group, they are close in size, so it is electronegativity that controls how acidic the acids are, and how stable the conjugate base anions are. The huge equilibrium constant aligns with the idea that an oxygen anion is much more stable than a nitrogen anion, because oxygen is more electronegative and is more attracted to electrons. So, to explain this reaction pathway, we know that electron-rich anionic nitrogen on the left is attracted to the electron-poor hydrogen on the alcohol. The nitrogen attacks the proton, and the OH bond is cleaved to avoid breaking the octet rule. The negative charge is then deposited on the oxygen, which makes it more stable. As we begin to quantify acid strength with pKa values, we will find that alcohols have a pKa of about 16, while amines have a value of around 38. Anionic amines are therefore an excellent choice of base for deprotonating alcohols. The acidity of a species in a row of the periodic table is therefore related to how positive the proton is in the acid, and also how stabilized the conjugate base is, based on electronegativity. When we turn our attention to atoms that are collected on the periodic table in groups, such as oxygen and sulfur, it becomes obvious that electronegativity doesn't explain the observed acidities. The sulfur acid, a thiol, is much more acidic than the alcohol, with a pKa value of around 10 versus 16. This is despite oxygen's electronegativity being 3.5 and sulfur's being 2.5. There certainly won't be a significant dipole between S and H. We do know, however, that the S to H bond should be weaker than the O to H bond, based on atoms of quite different size not having efficient orbital overlap. Swapping the SH bond for the OH bond should therefore be desirable in terms of enthalpy. The OH bond is, in fact, over 30 kilocalories per mole stronger than the SH bond. The major factor in play here is the atomic size difference, with the significantly larger sulfur atom being able to spread the charge better over its surface area than the smaller oxygen. This is a general idea and explains, for example, why hydroiodic acid is so much stronger than hydrobromic or hydrochloric. In this example, we have to consider one oxygen species, deprotonating another. This means we can't use electronegativity, or atom size, to explain the observations, since we are just dealing with oxygen. The fact is that when the alkoxide base reacts with the carboxylic acid, the reaction goes completely to the right, and there is no equilibrium. We can begin to explain this by comparing the carboxylic acid on the left to the alcohol conjugate acid on the right. The carboxylic acid has a pKa of around 5, whereas the alcohol is around 16. That's a large difference for acids based on the same atom. The carbonyl group in the carboxylic acid is electron withdrawing, so the proton on the carboxylic acid should be more electron deficient than the one on the alcohol. The very large pKa difference, though, is also explained by where the negative charge, in the anionic bases, is better able to spread out. The carboxylic acid conjugate base is so much more stable than the alkoxide, because of its ability to spread the electron excess through the carbonyl pi system. The carboxylic acid is therefore much more acidic than the alcohol. In general, any acid whose conjugate base may be stabilized by resonance will be a stronger acid than one that cannot. Here we have a carboxylate anion deprotonating a carboxylic acid. So, not only do we have the same atoms involved, as in the previous example, we now have the same functional group on both sides of the equation. We therefore need to dig deeper to explain the fact that the fluorinated acid is stronger, and the reaction favors the right-hand side. The fluorinated carboxylic acid has a pKa value of 2.66 versus the acetic acid on the right, which has a pKa value of approximately 5. So how does adding a fluorine atom make that acid 100 times stronger than acetic acid? The fluorine is highly electronegative and pulls electron density towards itself and away from its neighbors. This makes the proton on the fluorinated acid more positive and therefore more attracted to base. On the right-hand side of the equation, the fluorine helps spread electron density in the anion, thereby stabilizing it. This is not through resonance, but through induction, which spreads electron density out through single bonds. This effect can be quite profound, with trifluoroacetic acid becoming strong enough to have a negative pKa. The last main factor to consider in acid strength is the hybridization of the atom, attached to the potentially acidic proton. The proportion of S character in a bond will have something to say about bond strength and also conjugate base stability. This becomes obvious when we consider the pKa values of simple hydrocarbons. Methane, and alkanes like it, have exceptionally high pKa values around 50, and they are not considered to be acidic at all. Considering there is no dipole between C and H, a base would not be attracted to the proton, and the charge in the anionic conjugate base would be on carbon with its low electronegativity. When we move to alkenes, the pKa drops to around 44, so the acid is stronger than an alkane, but still very weak. This is accounted for by the sp2 carbon being able to handle the negative charge better, since S is more electronegative than P. The pattern continues as we move to alkynes, where the pKa drops to around 25. This is a dramatic change from the alkanes, with the sp hybridization, and its 50% S character, making alkynes 10 to the 25th power more acidic than alkanes. So, we now have criteria for assessing acid strength. Begin by considering the relative electronegativity, or size of the atoms involved, and if that doesn't solve the problem, look for the potential for resonance in the bases. If you need to go further, look for any potential inductive effects, and, finally, whether hybridization plays a role. Having summarized what contributes to acid and base strength, it will be important to pick up a series of pKa values so we can use them to solve problems in organic chemistry. We must remember that pKa is derived from acid equilibrium constants, but is a much easier set of numbers to assimilate. In general, the lower the pKa, the stronger the acid, and the higher the pKa, the weaker the acid. The mineral acids that you are familiar with from general chemistry are extremely strong acids with negative pKa values. These acids will protonate all kinds of bases and will prove to be exceptionally useful in organic synthesis. Next, the hydronium ion, with a pKa of -1.7, shows up in many mechanisms as the conjugate acid of water. We will be able to relate this to protonated alcohols, and knowing this number in relationship will make many second semester mechanisms much easier to manage. Moving to the carboxylic acids, the unsubstituted compounds start out with a pKa around 5. Adding electron withdrawing groups will lower the pKa, and these carboxylic acid molecules tend to be some of the more acidic, organic compounds found in this course. Phenols are a special class of alcohols which benefit from extensive delocalization in their conjugate bases once deprotonated. As such, their pKa values begin around 10, and phenols are readily deprotonated by bases we will encounter as reagents. Water and simple alcohols have pKa values around 16, which means they are weak acids that will take a strong base to deprotonate. Moving to terminal alkynes, we meet the first of the very weak acids that are actually very useful in synthesis. While a pKa value of around 25 means these molecules are very weak acids, there are plenty of bases that will take the terminal proton off and then provide very useful reagents for making extended carbon chains. One of the least acidic functional groups that is typically encountered in the organic sequence is amines, with pKa values around 38. Like alkynes, these weakly acidic molecules may be deprotonated with strong bases to provide useful reagents for synthesis. Finally, alkanes are not acidic, as gathered from their extremely high pKa values that are actually difficult to measure. Their conjugate bases, though, are very useful reagents that will be used to deprotonate weakly acidic molecules, such as amines and alkynes.